Imagine a world where numbers are not just about counting or calculating quantities. Instead, they become tools for unlocking hidden symmetries, solving complex puzzles, and revealing the secrets of mathematical structures. Welcome to the world of abstract algebra. Why is abstract algebra relevant outside the math classroom? Well, you would be surprised. From cryptography to computer science, physics to engineering, abstract algebra plays a vital role in solving complex problems and understanding the world around us. So, get ready to embark on a mathematical adventure as we explore the beauty, complexity, and real-world impact of abstract algebra. Whether you're a math enthusiast or just curious about the world of numbers, this journey will be both enlightening and exciting. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the Abstract Algebra Explained, the elegant world of abstract algebra, a comprehensive introduction. Well, before we go ahead and learn more about abstract algebra, the first thing that we need to know is understand that what is abstract algebra. Before going ahead and giving you a mathematical understanding and a definition, here is a quick and easy understanding in plain and simple English. As you see, it tells that abstract algebra is a branch of algebra dealing with the study of algebraic systems or structures with one or more mathematical operations associated with elements with an identifiable pattern differing from the usual number of systems. Now, this definition is very important, the very basic foundation concept. You have seen that I have underlined already algebraic systems or structures. This is very important. We get something which is an algebraic system as well as a structure. We also get something which is called one or more mathematical operations, and we get something very important, that it is associated with identifiable pattern and which is a little bit different from the usual number systems. 1, 2, 3, 4, these are the prime core 4 elements which I will take forward and make you understand, because these are the core and the basic strong foundation of abstract algebra. However, this is also a very simple definition that abstract algebra is a branch of mathematics which deals with algebraic structures and operations in a broad and generalized way. Now, this is important because we are dealing with something which is a broad and generalized, and it focuses on studying mathematical systems and their properties without necessarily relying on specific numbers. Now, you see, we are already differing from the conventional algebra. We are not relying on specific numbers. Instead, we are depending on certain abstract sets and operations defined on them. So try to understand that at its core, abstract algebra is all about exploring and understanding abstract mathematical structures. It is like peeling back the layers of everyday numbers to uncover the underlying rules and patterns that govern them. That means we are going much more deeper than the general algebra. So first, what we would do is that we'll try to understand what do we mean by algebraic system or algebraic structure. Now, here is a quick definition, but before going ahead with the definition, I would like you to look into this schematic diagram. First is that it says that an algebraic system is a mathematical structure. So here it is, it should have a mathematical structure. Then it should have a domain, as the definition tells that it consists of a set called the domain and one or more operations on the domain. So these operations like plus, minus, etc. Now, the operations can be unary. That means a single operation. For example, square root of 16 is 4. It can be binary, which takes 2. 2 plus 3 equals to 5 or so. And it can be n-ary. That means it can take up to n operations. For example, sigma I of x goes up to xn. So this is what we called is an algebraic system or a structure. There will be a mathematical structure. There should be a domain, and it should have mathematical operations which can be unary, binary, or n-ary. Now, there are some more examples of what we call algebraic structures. Let me tell. So we can say that it is a set of objects with one or more rules which combine this object. These rules can be called axioms, or they define, to say how they actually combine to form the objects. Now, specifically, we can tell there's this algebraic system or structure contains number one, what is called a group. which is a kind of a, say for example, a group of people which contains one binary operation that is associative and has an identity element and has inverses for all elements. Second thing, it is also have something which is called a ring. Rings are also algebraic system, but it has got two binary operations, addition and multiplication, and they would certainly satisfy A, B, C, D or whatever the axioms. Then we have something which is called a field, and fields are algebraic system with two binary operations. And then we have something which we already know, that is called vector spaces, which are algebraic systems with two binary operations, addition and scalar multiplication, and obviously that also has to follow certain axioms and rules. Now, taking this thing together, I would also like to show you further few examples of algebraic system. First is this one, which is called the set of all integers, which is denoted by this one, with the binary operation of addition is an algebraic system. So this is an algebraic system. The addition operation is associative, has an identity element which is typically 0 and has inverses for all elements. For example, the negative of an integer in its inverses. Now, this is also an algebraic system R. This is a set of all real numbers with two binary operations of addition and a multiplication. This is also an algebraic system. The addition and multiplication operations are associative, have identity elements, and also have inverses for all elements. The negative of a real number is its inverses, and so on. Now, apart from this, say for example this one, the set of all matrices of a fixed size. This is also an algebraic system with the binary operations of addition and multiplication. This is an algebraic system. So the addition and multiplication operations are associative, have identity difference, and have inverses for all elements. For example, invertible matrices. So as you can see here, R, x1, x2, x up to go xn, these are the matrices of the fixed size. And it also says that the set of all polynomials in a fixed number of variables with the binary operations of addition and multiplication. Now, this is actually what we call is an abstract algebra. What is an algebraic system? Now, I would like to show you, these are all English, we understand partly with some equation, but I would like to show you that what is actually an algebraic system in a very simple manner using a very simple equation. Let us look in the next part of our video. So algebraic system, here it is, are used in many different areas of mathematics, including number theory, geometry, topology, and so on. So here is a simple equation and it will explain you what is an algebraic system. So for example, we are about to find out the solution for this equation, x squared plus 2x minus 3 equals to 0. So what we can do is that we can use the properties of the real number system, which is an algebraic system, to solve this equation. So for the solution to the equation will be, we can factorize x plus 3x minus 1 equals to 0. So what we see from here is that this means that either x equals to x plus 3, or x will be equal to x equal to minus 3, or x equal to plus 1. That means that either this one, x plus 3, will be equal to 0, or x minus 1 equal to 0. Therefore the solutions would be x minus 3 and x1. Now this is something which is called an algebraic system. So this algebraic system, which we solve very easy, I mean to say class level, basic school level mathematics, but this is also an algebraic system which shows that it will have a solution either equals to minus 3 or positive 1. So this is a powerful tool for mathematicians and scientists, and there is used in different types of researches. Now you might now have a question that I talked about algebraic system as well as algebraic structure. Now is it that algebraic system or algebraic structure are the same or are they different? Then why we are using those two different terms? Let us look into this subtle difference in the next part of our video. What is an algebraic system and what is an algebraic structure? So the question rises that is algebraic system or algebraic structure same? So the clean answer would be yes. But I would say they are used interchangeably. Now they actually both refer to mathematical structure consisting of a set called the domain and one or more structures of the domain. So here it is. This is a mathematical system, the green one, and then we get a domain, which is this yellow one, and then there are operations and there are certain axioms. So taking this particular schematic diagram, we can tell that basically they both refer to the mathematical structure, as you can see, the green one, and of a set called the domain, which is the yellow one, and it will have one or more operations which I have highlighted, and the operation must satisfy certain axioms which are the properties of the operations. So now the question is that some authors make a subtle distinction between the two terms, with algebraic system sometimes referring to a more general class, broad class. As you see, algebraic structures are more broad. For example, it is used for groups or rings or fields, and I can say algebraic system is more to emphasize the system's operational and structural aspects. So some mathematicians might prefer the term algebraic system to emphasize the system's operational and structural aspects. Some mathematicians or authors, they emphasize on the term algebraic structures, which refers to more specific classes. However, the distinction is not widely accepted, and the two terms are used almost synonymously and I would say interchangeably. So you understand what is an algebraic system, what is an algebraic structure. Now we come to the most important part, the basic fundamental, or I would say philosophical aspect of understanding abstract algebra, is what are called algebraic patterns. Now you see, there are numerous type of algebraic patterns, as you can see, collecting these dots, these cubes, etc. So there are different types of algebraic patterns. So what do I mean by algebraic pattern is this one. So it is a mathematical pattern which is a regular and a systematic arrangement, and it follows a specific rules and it undergoes an iteration, isn't it? There has to be a kind of a systematic arrangement, and the shapes will follow a specific structure. Now algebraic patterns actually is the, I would say, pivotal force behind the entire mathematics of abstract algebra. Because remember, right at the beginning I told you that we are not dealing with more of numbers, but rather identifying the underlying patterns. So what does those patterns help? I mean to say, mathematical pattern is there, but what does it help? First is that it helps in problem solving, because patterns help mathematicians identify relationships and regularities within problems, making it easier to find solutions. Recognizing patterns is a fundamental, I would say, step in solving mathematical problems. Second is generalization. Very important. Understanding generalization allows the mathematicians to make generalizations and develop theories that applies to a wide range of solutions. Third would be underlying structure of mathematical concepts. This is very important because we need to understand the patterns can be abstracted to create mathematical models, making it easier to understand the real world phenomena. These are especially important in physics, engineering, and statistics, and making predictions about the future behavior. Because until and unless we identify patterns, new discoveries and new forecasts, this won't be done. So this is, I would say, a very important aspect, that why do we understand algebraic patterns? To solve problem, to generalize and make it more applicable to a wider range of physics and mathematics, understand the mathematical concept and make a prediction about the future behavior of the model. So from here what I see is that this is a Pascal's triangle. I mean to say, everybody knows that, and this is the Fibonacci series. So these are basically, I mean to say, patterns. These are patterns which are extremely important, extremely beautiful, and until and unless we understand abstract algebra, we won't be able to understand these patterns. And these patterns are something very fundamental and helps us to understand the philosophy of mathematics. Now you see, in algebraic patterns, generally refer to systematic arrangements that follow a relation. So what we can generally say, I mean to say, if we take the mathematical algebraic pattern, then we can say it has got something which is called a repetitive structure, because these are recurring sequences, right? Arrangements or behaviors in algebraic expressions, equations, or algebraic system which keeps on repeating. Number two is that regular operations. Patterns also involve the application of mathematical operations like addition, multiplication that follow specific rules. Third, what it comes is structural relationships, because patterns can be related to the overall structure of an algebraic system, including the way elements interact with each other and mathematical operations. And the last one, most important, is the symmetry. Yes, symmetry patterns are common in group theory, a branch of abstract algebra where we study the elements exhibiting specific symmetrical properties under, I would say, defined operations. So repetitive structure, regular operations, structured relationships, symmetry, all of this can be finally summarized into a commutative property, an associative property, a distributive property, an identity element, and inverse elements. So I mean to say, all of this the right hand side has got repetitive regular structure relationships and symmetry. So from here, what we turn our page, we find that these are the four things, and most importantly these properties are very, very fundamental in arithmetic and algebra, and it includes field and ring theories. What is also important, take a note that they are often granted in everyday mathematical operations, but are foundation principles that help simplify mathematical calculations. You take it for granted, but these are very important, very fundamental. So for example, if I take an even number plus even number gets an even number. So what are we doing? That is what it is called. It is a pattern that holds for many different, I would say, structures, including groups, rings and fields. So on the left hand side, I've just given a schematic diagram of a structure, but even number plus even number gets an even number. So that is also kind of a pattern. Is also kind of a system which can be generalized and used. So the question is that from here, where do we actually go? So what does those actually mean, and what is the real significance of patterns and how it is important in abstract algebra? Let us look in the next part of our video. So if I take this kind of a pattern, say for example 18 minus 3 15 minus 3 12 minus 3 9 and so on, then if I take the positive part, we get something like this, right? 18 plus 3 plus 3 plus 3 and so on. Now from here, what I can say is that this is something that we can model out to find a similar pattern, obviously. And this would be helpful because I can then forecast that the next number would be 33, 36 and so on. And what is important is that it would help you to understand the very basic, the deep underlying nature of that model. I mean, it's a fractals have got nice patterns. So all those fractals, Mandelbrot said, these are nothing but patterns. And this model, this is the way abstract algebra helps us. And what it actually does is this one, generalization. Most important factor. Generalization actually helps us to create a broad and general mathematical model. It also helps us to generalize into broader equations and innovate new and bigger and broader theorems, which would ultimately help us to create a better mathematical model. As you can see here, all those eminent physicists starting from Newton to Abdus Salam, Steven Weinberg, Maxwell and Einstein, what they all did, generations after generations, year after year and so on, they actually created generalization. They actually created mathematical model. They actually generalized Newton's equations to relativity, then Maxwell's equation into special relativity, then further into grand unification theory, electroweak unification and so on. And if you're now feeling a little bit curious, what is this all about? Look into this video of mine, Generalization and Unification. This is a video which I made a few months back, which is called Unification Theory and Theory of Everything, which speaks about all those unification, all those which ultimately united, and we are finding a theory of everything. Okay, so far so good. So we go to the next page where we define this, that now we again let us revisit the definition which we have done. So you see, abstract algebra is a branch of algebra which deals with algebraic system. We know what is an algebraic system, isn't it? And we also know that algebraic system and structure, how they are different and similar. We know that it will carry one or more mathematical operations, and we also know there would be an identifiable pattern which is not usually the number system but something even deeper. So here is the summary. We can say, I'm sorry, it should be say, rather than relying upon the operations, abstract algebra reside most on the structures, patterns, and the focus is basically to understand the underlying structures and properties of these abstract systems. Now the question is that we are continuously saying what is abstract, abstract and abstract. My question to you is that what is abstract and why we called abstract algebra as abstract? Coming up in the next part of the video, why we call abstract algebra as abstract. Now, before going into this very important topic, I would say algebra, not coming to abstract algebra, algebra itself is abstract. The fact is that when you first start watching this kind of an equation, fx equal to this, then you go into this and into this, what you're doing is that you're already taking a first step towards abstraction. because x and h and k and to the power of 3, these are something which you do not see in everyday life. These are something which you do not encounter in your daily life when you go to your college, when you visit the universities, when you're taking a day out with your family. Do you see x cube or fx or square root of x? No. That means you have already taken a step towards abstraction. So algebra itself is abstract. So obviously abstract algebra will be abstract. So this is the first step towards learning abstraction. It helps to simplify complicated problems, and it helps you to understand the relationship which we're talking about, different patterns. And on this topic, I've already made a video which is called How Algebra Improves Critical Thinking. This is a very good video. It is there in Physics for Students. You can just go and check it. It will be important for you to know that how and why algebra improves critical thinking. So what we do is that now I will try to define why we called abstract algebra as abstract. I will take basically two instances. I will first take what is known to us, that is called a vector space. So abstract algebra is abstract because it studies the underlying structure of algebraic objects. Okay, so let us take a vector space. Now what I'm trying to tell you over here is very important. Now once we define a particular concept in vector space, in abstract algebra in different ways, and it actually gives us an advantage to know more about its underlying structure. So vector space, first of all, can be defined in terms of geometric representation. So in geometric terms, we say vectors can be represented as directed line segments in general Euclidean space. So each vector has a magnitude, a length, and a direction. We know that. And this representation is useful for visualizing vector and vector operation, especially in 2 and 3 dimensional space. The second is the linear combinations. So you can arrange vectors like 1, 2, 3, 4, 5, 6 and 1 plus 2, 4t and so on with some real number. So you see what I'm saying, that why it is abstract. It is abstract because of this. If you define a particular concept in so many number of ways, then it will become abstract. And because you can define a concept in so many ways, it becomes very important, very robust and a rigid mathematical tool which you can use later. We'll see next. For example, a matrix. A matrix is a rectangular array of numbers. Now, matrices can be used to represent linear combination. For example, right on your screen, you can see A equals to 1, 2, 3, 4 can be used to represent the linear transformation that takes vector xy into x plus 2y and 3x plus 4y. So this is one. So again, you see the third representation of vector space is in terms of matrices. We can also represent in terms of polynomials. For example, if I take the polynomial this one, px is equal to x square minus plus 3x plus y, then it can be represented by the coordinate vector 2, 3 and 1. So 1, 2, 3, 4, this is another way of representing vector space. Also what we can do is that we can define vector space in terms of fixed numbers. So if we get A as 1, 2, 3, 4, then we can define it again as this. So what my point I'm trying to tell you is that, see, vector space itself is a concept of abstract algebra. And now when I have defined 1, 2, 3, 4 and 5 ways, that means we have generalized and made it so abstract that it is now become a robust mathematical tool which can be used in geometric representation, linear combination, matrices, vectors and in matrices also. I will take one more example in the next part of our video, which is called a group. Don't worry if you don't understand group theory, this is just a kind of an, I would say, a basic understanding. So if I take a group, say for example G, first of all I can represent it as Cayley table. Simple. It's a square table that lists the results of performing the group operation on all parts of the elements in the group. So this Cayley table for the group is under addition as it is shown here. The second thing which I would show is called generator relation presentation. So if for example the cyclic group of order 3 can be represented by the generator G and the relation this one. The third one would be homomorphism. So what we mean by homomorphism, basically a map between two groups that preserves the group operation, isn't it? So if I take a map phi x equal to this one, x square, then obviously it is homomorphism from the group of integers under addition to the group of integration under multiplication. So 1, 2, 3. So group is also getting so many different dimensions. That means it is very abstract. And because it is very abstract, it is rigid, it is great, and it is robust, and it can be used for other areas. It can also be used for the rotations of a group rotations of a cube. We can also use for the group of permutations of a set, and we can use it for group presentation. So for example, if a group presentation for the cyclic group of order this one, then what we can do is that A generates the group and it becomes this one. So the basic point what I am trying to tell is that abstraction is the fundamental tool in mathematics. By abstracting away the specific details of a problem, we can focus on the underlying structure and develop more and more powerful theorems. Just like as I showed with vector space, just like as I showed with group theory, these are all abstract concepts, and that is why abstract algebra is called abstract. And because of this abstractness, it becomes so robust, so strong that it can be generalized to other areas. So it is generalized and applicable to a wide range of scope. Why we call it abstract? Why? Because by abstracting the specific details, we can focus on the more general and powerful theorems. Also, point number 2 is that why it is abstract? Because it is abstract and hence it is generalized. Because abstract algebra deals with studies of abstract algebraic structures, and it generalizes and abstracts away the specific operation and it concentrates on specific tools. Also, I would say that if you see that because it is abstract, it is universal. Now, until it becomes abstract, until it is applicable, how can we tell that it is universal? As you saw, vector space and group, these are universal and it is representing so many dimensions. So, considering, say for example, this one, emphasis on structure, abstract algebra is more interested in the structure and properties of the algebraic systems rather than the values that are involved. So if I consider the set of all integers, for example z, with the binary operation of addition, then this set, this z, forms a group, right? Binary operation addition, it forms a group which is an abstract algebraic structures. And the specific integers in the set do not matter. Remember, the specific integers in the set do not matter. What matters is the structure of the set and the way that addition and operation takes place. Again, I repeat, this is Z is basically a set of all integers with the binary operation of addition. This set forms a group which is abstract in algebraic structure. The specific integers in the set do not matter. What matters is the structure of the set and the way that the addition and operation works over there. Now that we have talked about why we have understood abstract algebra, we have also understood that why it is abstract. Now there are different branches of abstract algebra also. That is something we need to understand. Here it is, most important fact. In the set, specific integer doesn't matter. It is the structure of the set which matters. Now the thing is that we talked about abstractness. Now it is a time that we should know what are the different branches of abstract algebra. Although it is huge, but I will try to cover and give you most important abstract algebra branches and touch on the very important parts in the next part of the video, branches of abstract algebra. Now the thing is that if I divide abstract algebra, it would take a whole night today to explain all that. But the first thing would be the group theory. Now in abstract algebra, it is like a set of rules, remember, for studying objects and their symmetries. Simple. It helps us to understand how things can be combined, inverted and related in a systematic way. That's it. It is a study of rules of symmetries, and it helps how things combine inverted in a related system. Second is called a ring theory. This is in abstract algebra is a set of rules for dealing with numbers and operations. Now in ring theory is a structure where you can add and multiply numbers, and it follows obviously certain rules. So rings helps us to study things like equations and polynomials, and it is a fundamental concept in algebra. Third is called the field theory. This is like a special type of number systems. In a field, you can do addition, subtraction, multiplication and division just like with regular numbers, but obviously there are specific rules and you must follow. Fields are important because they provide a solid foundation for solving equations and work with fractions. Then comes module theory. This is in abstract algebra is a bit like I would say a bridge between vectors and rings. So it helps us to understand how to work with things that combine properties, numbers and vectors, etc. we move on to the next page, and what we already know, I don't need to explain much. This is vector space. This is actually the playground for vectors, which are just arrows with certain rules, and it is a space where you can add and stretch and do all those vectors. Next comes lattice theory. This is in abstract algebra, is a way of organizing and studying relationships between different items. It is like arranging objects in a grid of network where there are the rules for combining and comparing these items. Commutative theory. This is in abstract algebra, focuses on operations like addition and multiplication, but the order of the elements hardly matters. It does not matter. In simple terms, you can say it is about math operations that are like commute-friendly road. It does not matter whether you can add or multiply things in order or the other. Then comes category theory. It is like a big picture of looking at mathematics. It does not focus on numbers or specific structures, but instead it looks on how different mathematical things are connected and interact. Then comes representation theory. It is, I would say, is like translating mathematics into different languages. It is a way to study abstract algebra structures like groups and bialgebras. Now, as you can see that these are basically the different branches of abstract algebra, and the problem is that each of these would require a separate video, a separate understanding, a separate, I would say, a way in which we can do. But I would like to take a pause over here, and that is all about abstract algebra. Few more are left. One is called the homotopy theory, which is a branch of algebraic topology that studies topological spaces. Galois theory, very important, is the study of field extensions, I would say, which contain smaller fields. Galois theory has many applications. Then comes what is called a non-associative algebra, which explores algebraic structures that does not satisfy the associative property. And then comes a homological algebra, which is further advanced part, which focuses on homology and cohomology theory. And I would say the list goes on and on and on. It is very difficult, as I told you, to focus and tell you in short. So this is in all what we called is are the branches of abstract algebra, and in very simple language what it is all about. Now what I would like to show you is that we talked about abstract algebra, we talked about what is algebra, we talked about the abstractness, patterns, everything. But what we did not talk about is that it is all okay, but how it helps in calculations, how it is different from the normal or elementary algebra. In one way we can say what is the power of abstract algebra, coming up in the next part of the video, how it is different and what is the power of abstract algebra. I will use specifically two ways in making you understand about the power of abstract algebra. First is that I will use a group theory, and then I try to demonstrate with Galois theory. Suppose I have an equation like this, and I can say that this equation is actually true for all groups, and you already know there is something which is called a left cancellation law. Now if I want, so that means what? That A multiplied by B, A inverse equal to B. This is a left cancellation law. Now this law is applicable to all groups. Now say for example I have an equation Ax equal to B, and I am trying to solve that. So if I take the steps, I would do this, I will take the inverse, and then I will do this, and then the next step would be E, and this E is nothing but it is the identity element, because you know that since any element in E multiplied by another element gives equal to X, so we will get this one, X equal to A inverse of A multiplied by B. Now what we saw over here is that, okay fine, so this actually has a solution for the equation X equal to B. Now the question is that what about equations which does not have a solution? For example, let me show you this example. Say for example AB multiplied by BA. It is simple. It doesn't matter in which order these things are multiplied. Now this can be used for commutativity of addition, multiplication of real numbers, commutativity of rotation, reflection, symmetries, everything. Right? So this is something we can say that if I apply this as a group, then the power of abstract algebra tells that this can be applicable to 1, 2, 3, 4, and the order does not matter, and it is applicable to any sort of a group. Now on the other hand, if I take this one, 2 plus 3, 3 plus 2, here also the order in which they are added doesn't matter. But what if I try to measure or make this to infinite amount of numbers? Remember, this is valid only for specific numbers. Now, if we want to represent this commutativity of addition or the above multiplication for all real numbers, then we have to keep on adding, multiplying, adding up till infinity. So this is what is called the power of abstract algebra. We create a group, we set a law, and then it is applicable to everywhere. Okay, now let me show you, this is another advantage. That means we can use abstract algebra to prove theorems. For example, I have a theorem like this. Just hypothetical. Inverse of an element is unique. What does that mean? That means that this theorem can be used to prove any or many other theorems of this group. So as we told that in abstract algebra, we create a group and then we define these certain axioms or a set of rules, and these rules become permanent to them. What about this theorem? Say for example, the sum of two positive numbers is a positive number. Again, if you want to prove this theorem for a different set of numbers, such as a complex number, we would need to use a different proof. So this actually shows the power of abstract algebra, defining a particular theorem, extending and generalizing it. Okay, this is the famous, I would say one of the greatest ever talented young mathematician ever is the Galois. Now, I want to demonstrate the power of abstract algebra using Galois theory. Simple. Now, if you get an equation like this, now we can factorize this equation, and what we get, that this is a solvable equation, right? This is absolutely solvable. This is very simple. But what if we get this kind of an equation? Now, in this equation, what we see, this is not easy to solve, and it uses regular algebraic methods. So Galois theory will help us to understand why some equations are solvable, why some equations are not solvable. It does this by studying the symmetries and the roots of the polynomials. So this is again this Galois theory of abstract algebra. This is the power that it helps us to understand which one is solvable, which one is not solvable, what is the symmetry, understand. So it helps us to understand and answer questions like why we are able to find these solutions. Why can we prove that certain equations are unsolvable, and are there equations where we cannot find solutions? So this is what actually is the basic power, the basic idea that I was telling, that the power of abstract algebra, how abstract algebra is different from elementary algebra. This is how it does. Now, having said the power of abstract algebra, now it is the time that we need to understand that why do we need abstract algebra? I mean to say, what if that we do not have abstract algebra, coming in the next part of the video. The first thing, as I already told you, very important, is generalization. Because without generalization, we cannot make a proper, robust mathematical theory, a rigid theorem, or so on. The second is to understand the structure and symmetry. Obviously, it would help us to understand the underlying structure, like Galois theory or group theory, and then only we can move forward. It is also important because cryptography actually uses a lot of abstract algebra, and it helps to secure data in every other way. Coding theory, this is using a lot of vector spaces, fields, etc. And most importantly, quantum mechanics also uses group theory to describe the behavior of particles. Now we have got something which is called an automata theory, which is topology, which is very important using abstract algebra. A group theory and chemistry using gene structures, etc. uses that. The mathematical logic, the foundation, the understanding of the logic uses abstract algebra. Number theory, statistical analysis, most importantly uses abstract algebra, because a lot of data needs to be formulated in a particular model, in a particular theory, in a particular structure, so that we can make those things happen, so that we can create more and more generalized statistical models. And from these models, what we can do is that future forecast of the market, share market, anything. So as I told you, now you see right at the beginning, that helps in forecasting models, it helps in creating models. Why? This is the basic idea. So statistical concepts and statistical ideas actually helps you to create this type of models. So what we can say is that machine learning machine learning and data science nowadays. I went to Bangalore a year back, and I was astounded to say that is a huge number of data science is using abstract algebra. So to summarize, what we can say is that abstract algebra serves as a unifying framework for a diverse range of mathematical disciplines, and enables the exploration of the fundamental structures and properties of mathematical objects. So here is a quick summary of what we learned today. We learned what is abstract algebra, algebraic system and structure, what is algebraic pattern, why patterns are important, why abstract algebra is called abstract, the power of abstract algebra demonstrated in group theory and Galois theory, and what are the practical applications, why do we need abstract algebra at all. So that's all for today's video. This is just an introduction to abstract algebra without covering any amount of mathematics, without covering any group theory or ring theory, just to give you an essence and underlying the deep mathematics and the beauty and the philosophy of abstract algebra. So that's it for today's video. If you have liked the video, please do subscribe to my channel Physics for Students and hit on the subscribe button. I thank you immensely for taking up the time to watch this video. This is my contact number, and this is my other channel on general theory of relativity. You can subscribe to this other channel and follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with more videos in order to enjoy, engage and understand the beauty of physics and mathematics. But till then, goodbye.